everyone's watching the wrong thing, Comet C 2026. A1 is diving toward the Sun this April, and yes, it is a beautiful show. But here is what nobody is saying out loud. That comet poses zero danger to Earth. Zero. The real threat is not the thing getting all the attention. It is a 340-meter asteroid named after the god of chaos, quietly closing in for the closest flyby in recorded history. In 2029, Apophis will pass between Earth and our own satellites, close enough to see with your naked eyes. On a Friday the 13th, it once had a 2.7% chance of hitting us. 3 spacecraft are racing to meet it, and one of them almost got cancelled. Stay until the end. This isn't about the comet, it's about the real threat we're not paying attention to. If this has you hooked, subscribe to the Skylab, because as the night sky gets more crowded with objects we're only beginning to understand, and the science of planetary defense races to keep up, we will be here reporting on all of it. Drop a comment telling me where you're watching from, and tell me honestly, do you think the Apophis flyby is just a harmless cosmic coincidence? Or do you think the universe is giving us one final dress rehearsal? Now, let's get into it. Part 1. Everyone's watching the wrong object. Right now, millions of people are staring at the wrong thing. Somewhere across the internet, on live streams, in astronomy forums, on social media threads that somehow went viral, the conversation is dominated by a comet. Comet C/2026 A1, discovered in January of 2026, is currently falling toward the Sun at extraordinary speed, and the world has decided this is the most fascinating thing happening in the sky. People are setting calendar reminders, amateur astronomers are positioning their telescopes. The comment sections are full of one question, over and over: will it survive? And look, that is a fair question. It is also, when you zoom out a little, a beautiful distraction. The comet belongs to a rare and violent family called Kreutz sungrazers, a class of comets that do not merely approach the Sun but genuinely plunge into its outer atmosphere. We are talking about an object hurtling toward perihelion on April 4th, 2026, passing only approximately 163,000 kilometers above the solar surface. That is inside the Sun's outer corona. The corona. The comet will be flying through the Sun's own atmosphere, and people are watching from Earth wondering if it will come out the other side glowing brighter than Venus, or simply cease to exist. That drama is real. The spectacle is genuine. If C/2026 A1 survives, it could become one of the most visually remarkable comets in a generation. But here is the thing nobody is talking about in those comment sections. The comet will pass Earth at a distance of approximately 143.8 million kilometers. That is almost exactly the distance from Earth to the Sun. It could not hit us if it tried. It is not trying. It is not even aware we exist. The comet is a beautiful light show with zero threat attached, and yet it has captured the full attention of the astronomy community and a significant slice of the general public. Meanwhile, something else is coming. Its name is 99,942 Apophis, and astronomers named it after the ancient Egyptian god of chaos, darkness, and destruction. That was not a casual naming decision. When scientists look back at the history of asteroid detection, Apophis represents a specific kind of alarm, the kind that gets passed quietly between researchers in the middle of the night, the kind that triggers emergency observation campaigns, the kind that briefly made planetary scientists wonder if they were looking at the end of a city, or a coastline, or something larger. On April 13th, 2029, Apophis will fly past Earth at a distance of approximately 31,600 kilometers above the surface. Read that number again. 31,600 kilometers. For comparison, the Moon orbits at roughly 384,400 kilometers. Geostationary communication satellites, the ones that make your GPS work and your television receive signal, orbit at approximately 35,786 kilometers. Apophis will pass closer to Earth than those satellites. It will thread the gap between our planet and our own technological infrastructure, and it will do this as a 340-meter wide rock, travelling at several kilometers per second. Roughly 2 billion people across Europe, Africa, and Asia will be able to see it with the naked eye. Let that picture form in your mind. A Friday the 13th in 2029. You walk outside after sunset, you look up, and there it is. moving visibly across the sky. Not a streak, not a flash, but a slow, deliberate point of light crossing the stars, a mountain-sized object passing through the neighbourhood of your satellites. No telescope required. This will be the closest confirmed approach of an asteroid this large in all of recorded history. The scientific instruments pointed at Apophis that day will rewrite what we know about asteroids. The spacecraft already en route to meet it will send back data that could define planetary defence for the next century. And yet right now the conversation is about the comet. There is something deeply human about that. We're drawn to spectacle. We're wired for the dramatic image, the visible threat, the thing that looks dangerous. A comet falling into the sun is cinematic. An asteroid you cannot see yet, arriving in 3 years, on a date that sounds like a horror movie premise, requires a different kind of attention. It requires you to sit with a number, to trust the math, to understand orbital mechanics well enough to feel the weight of what that flyby distance actually means. So why is the world watching the comet instead of the asteroid passing inside our satellite network? Part of the answer is visibility. Part of it is timing. And part of it is that most people do not know the full story of Apophis, including the part where it actually had a 2.7% chance of hitting Earth, where it briefly became the most dangerous object ever catalogued by modern astronomy, and where a measurement made in 2021 literally saved your life without you ever knowing it happened. That is the story worth telling. The comet will either survive April 4th or it will not. Either way, it will leave the solar system and never return. Apophis, on the other hand, is staying in the neighbourhood. It has already changed how humanity thinks about planetary defence. It is about to become the most studied asteroid in history, and the mission racing to meet it almost got cancelled by a budget line in Washington. We are watching the wrong object, but it is not too late to look up. Part 2. The comet that looks dangerous but isn't. The Comet sungrazer family has a history that stretches back more than 2,000 years, and it begins with an act of cosmic violence so large that we're still watching the debris fall. Sometime around 371 BC, astronomers believe a single enormous comet passed so close to the Sun that it shattered. Not evaporated, not faded, but fractured into thousands of pieces, each fragment inheriting the original object's orbital trajectory, each one now destined to fall toward the Sun in a slow parade across centuries. That original body was likely tens of kilometers wide. What it left behind became one of the most recognizable families of objects in the inner solar system. You have almost certainly never heard of most of them, because most of them are tiny, a few meters across at best, and they simply burn away long before they become impressive. But occasionally one of the fragments is large enough to put on a show. Comet C, discovered in 1965, became one of the brightest comets of the 20th century. Observers reported seeing it in broad daylight. Its tail stretched across a significant portion of the sky. It was, by almost any measure, spectacular, and it was a Comet sungrazer, a child of that 371 BC breakup, still falling along the original orbit more than 2,000 years later. The Great Comet of 1882 was another member of the same family, so bright that it was visible near the Sun during the day and left observers genuinely speechless. More than 5,200 Comet sungrazers have been discovered by the SO spacecraft alone. Most of them are small enough to completely disintegrate before they reach perihelion. They go in, they do not come out, and the only record of their existence is a brief smear of light in a space telescope's coronagraph image. C/2026. A1 is different, at least potentially. It was discovered at a distance of approximately 2.056 astronomical units from the Sun, farther away than any previously detected sungrazer at the time of its discovery. That matters because of what it implies about size. Smaller comets tend to become detectable only when they are much closer to the Sun, when the heat is already doing its work, sublimating ice and throwing off enough gas and dust to make them visible. Finding this one so far out suggests it might be carrying a significantly larger nucleus, with preliminary estimates placing the diameter at possibly up to approximately 2.4 kilometers. Those are preliminary numbers, subject to revision, but they are large enough to make astronomers pay attention. Now, what actually happens to a comet as it falls toward the Sun? The process is extraordinary to visualize. As the surface warms, the ice does not melt, it sublimates, transitioning directly from solid to gas without passing through liquid form. Those jets of gas and dust carry material away from the nucleus and form the coma, the fuzzy atmosphere surrounding the solid core, which can expand to sizes larger than some planets. The solar wind then pushes that material into the tail, which always points away from the sun regardless of which direction the comet is actually travelling. A comet heading away from the sun is still pointing its tail back toward the sun. The tail is not behind it, the tail is just away from the heat. For C/2026 A1, two outcomes are possible and only two. The first is survival. If the nucleus is large enough and structurally cohesive enough, it passes through the corona and emerges on the other side. The intense heating may strip away enormous amounts of surface material, but the core survives, and what comes out could be extraordinarily bright, potentially visible to the naked eye in the days following perihelion. The second outcome is disintegration. The tidal forces and thermal stress simply overwhelm the structure. The nucleus fractures, the pieces scatter, and the comet disappears. No dramatic explosion, no visible moment of destruction, just a gradual fading as the fragments disperse. Comet Ison in 2013 taught the public exactly how cruel this coin flip can be. Ison was hyped for months before its November 2013 perihelion. Headlines called it the Comet of the Century. Observers prepared for a sky-spanning spectacle. And then it grazed the sun and simply stopped existing as a coherent object. The post-perihelion images showed nothing where something spectacular had been promised. The Comet of the Century quietly dissolved into a faint smear of debris. So C/2026 A1 might be Ison, or it might be Ikea Seki. The honest answer is that nobody knows with certainty, and that genuine uncertainty is part of what makes it compelling. But here is what we do know with complete certainty. Even in the most dramatic possible scenario, even if C/2026 A1 somehow became the brightest comet in recorded history, it would still pass Earth at approximately 0.961 astronomical units. That is 96.1% of the average Earth-Sun distance, 143.8 million kilometers. It could not intersect our orbit no matter what happened at perihelion. The physics simply do not permit it. The comet is not coming for us. It never was. It is a passenger on a completely different road. The human brain responds to visual drama. A comet falling into the sun is drama we can picture, fire and ice, and a cliff-edge question of survival. The risk calculus for an asteroid flyby requires abstract thinking, an ability to feel the significance of a number like 31,600 kilometers without seeing a picture of it. We're not naturally built for that kind of fear. We are built for the spectacular, the visible, the immediate. And that tendency, that beautiful, ancient, very inconvenient tendency, is exactly how we almost missed the one that actually mattered. Part 3. The asteroid that terrified astronomers. On June 19, 2004, 3 astronomers working at Kitt Peak National Observatory in Arizona took images of a patch of sky and catalogued a new moving object. Roy Tucker, David Tholen and Fabrizio Bernardi were doing what asteroid hunters do, scanning the sky systematically, logging positions, filing the data. The object they found received the preliminary designation 2004 MN4, a perfectly unremarkable label for what appeared to be a perfectly unremarkable near-Earth asteroid. Nobody suspected, in that moment, that they had just discovered the most statistically dangerous object in the history of modern astronomy. Figuring out where an asteroid is going requires observations spread across time. A single night of data gives you a position. A week of data gives you a rough direction. Months of data give you an orbit. The problem with newly discovered asteroids is that you never have months of data when you first find them. You have days, sometimes weeks, and you're trying to extrapolate a trajectory from an extremely short arc of the object's actual path around the Sun. The uncertainties in those early calculations can be enormous. For 2004 MN4, astronomers began extending the calculation forward in time, projecting the orbit out toward known future dates, and somewhere in that process someone looked at the result for April 13, 2029 and stopped. The probability of Earth impact was 2.7%. That is 1 in 37 odds. To put that in perspective, if you roll a standard die, the chance of rolling any specific number is 1 in 6. The chance of Apophis hitting Earth was comparable to playing a version of Russian roulette with a 37-chamber revolver. Most people in that scenario walk away, but some do not. 2.7% is not a rounding error. It is not a data artifact. It was, at the time, a genuine probability produced by genuine orbital mechanics from genuine observational data. The Torino Impact Hazard Scale was created specifically to communicate these kinds of threats to the public without causing unnecessary panic. It runs from 0, meaning no hazard, to 10, meaning certain impact and global catastrophe. Most asteroids score 0 or 1. The scale is designed so that nearly everything sits at the bottom. Apophis reached level 4. Level 4 on the Torino scale is defined as a close encounter, meriting attention from astronomers. It represents a probability of collision large enough that public attention and governmental attention may be warranted. In the entire history of the scale, no real object had ever reached level 4 before. Apophis was the first. It remains the only asteroid ever assigned that rating and taken seriously as a genuine near-term threat. The response from the global astronomy community was immediate and intense. Observatories around the world began tracking Apophis around the clock. Scientists started searching through archives of old sky survey images, a process called pre-covery, looking for earlier photographs that might include the asteroid before its official discovery. Each additional observation extended the orbital arc, reducing the uncertainty, allowing the calculations to become more precise. Every new data point either confirmed the danger or began to narrow it away. Meanwhile, the public was processing something genuinely difficult to explain. An asteroid named after a chaos god had just been given the highest threat rating in history, and the date it might hit Earth was 2029. Not 100 years away, not 1,000 years away, 2029. People alive today, cities that exist now. The question was no longer academic, and then came the additional complication, because the story was not simply about whether Apophis would hit Earth in 2029. More observations began reducing that probability, but a new threat emerged from the orbital calculations, something subtle, something that required understanding, a concept most people had never heard of. The impact probability for 2029 was dropping, but 2029 was not the only date that mattered. The flyby itself, that terrifyingly close pass at 31,600 kilometers, would change Apophis's orbit. The question was by how much and in which direction. And there was one particular region of space, one specific corridor through the darkness, that if Apophis happened to pass through it during the 2029 flyby, would mean something far worse was coming later. Astronomers called it a gravitational keyhole, and the one associated with Apophis was only 610 meters wide. Part 4. The keyhole that almost ended us. A gravitational keyhole sounds like something from a science fiction novel, and the first time most people hear the concept, their instinct is to treat it as a metaphor. It is not a metaphor. It is a precisely calculated region in space, defined by orbital mechanics, where if an asteroid passes through during one approach to Earth, gravity will do the rest of the work automatically, redirecting the object onto a trajectory that leads to a direct impact at a specific future date. The keyhole is not where the asteroid hits. The keyhole is the door that opens to the room where the asteroid hits. For Apophis, scientists identified a keyhole associated with a potential impact in 2036. If the asteroid passed through a region only approximately 610 meters wide during the 2029 flyby, Earth's gravity during that close approach would subtly but precisely alter its orbit, and the result of that alteration would be an impact 7 years later, 610 meters. For reference, that is smaller than Central Park. That is a few city blocks of empty space, located tens of thousands of kilometers above Earth, and whether Apophis would thread that needle was, for a period of years, genuinely uncertain. Imagine trying to predict where a marble will land if you roll it across a gymnasium floor from 300 feet away, accounting for every microscopic bump and groove in the surface, and then telling someone whether that marble will eventually roll into a specific crack that is 2 inches wide. That is the scale of precision required to determine whether Apophis would pass through a 610-meter keyhole at a flyby distance of 31,600 kilometers. Scientists ran millions of orbital simulations. They mapped what astronomers call the orbital uncertainty region, the full range of possible trajectories consistent with existing observations, and they asked a single question over and over. Does any part of that uncertainty region overlap with the keyhole? For a frustrating number of years, the answer was yes. Part of the uncertainty came from measurement limits. Radar observations helped enormously, providing distance and velocity measurements far more precise than optical tracking alone could offer. Each radar ping from facilities like Goldstone in California or the Arecibo Observatory in Puerto Rico added another constraint to the orbit, shrinking the uncertainty region. The keyhole scenario slowly became less likely as more data came in, but there was a second, subtler source of uncertainty that radar could not fully resolve. It is called the Yarkovsky effect, and it is one of the more philosophically humbling concepts in asteroid science. The idea is this: sunlight carries momentum. When sunlight hits an asteroid, it exerts a tiny pressure on the surface. But the asteroid also rotates, and as it rotates, the side that was heated by sunlight eventually rotates away from the sun. That side is now slightly warmer than the dark side, and when warm surfaces radiate heat, they produce a tiny reactive force, like a miniature thruster, operating continuously over years and decades. The cumulative result of this process over long timescales can shift an asteroid's orbit by hundreds of meters, sometimes kilometers. For calculating whether Apophis would thread a 610-meter keyhole in 2029, a positional drift of even a few hundred meters in the asteroid's predicted location could completely change the answer. You cannot ignore the Yarkovsky effect when the keyhole is that small. Measuring it required knowing the asteroid's size, its shape, its rotation rate, its surface composition, its thermal properties, and its reflectivity. Some of those properties could be estimated. Others required dedicated observations. The whole situation created a frustrating loop. The orbital calculations were uncertain, partly because of the Yarkovsky effect, and measuring the Yarkovsky effect precisely required more time and more observations. The public struggled to understand why this was still a live question. Every time a news article appeared saying the threat had been reduced, someone would point out that the threat had not been fully eliminated. You can understand the confusion. Scientists were essentially saying, the asteroid will probably miss the keyhole, and therefore probably not hit Earth in 2036. But we cannot confirm this until we have measured a tiny thermal drift with radar precision. To most people, probably is not the same as safe. To scientists, it is a probability distribution with a confidence interval that was growing more reassuring every year. Both groups were right in their own frameworks. The keyhole concept did something useful beyond scaring people. It transformed how planetary defense researchers thought about threats. The question was no longer simply whether an object would hit Earth on a given date. The question was whether an object was approaching a gravitational corridor that could route it toward Earth at any future date. That is a more complex question, requiring longer time horizons, more observation resources, and more sophisticated modelling. Apophis essentially forced planetary defense to grow up. And then, in 2021, a measurement came through from 2 radio telescopes in California, and it changed everything. Part 5. The measurement that saved Earth. The Yarkovsky effect, as a concept, was proposed in the early 20th century by a Polish engineer named Ivan Osipovich Yarkovsky. He published a pamphlet describing the idea in 1902. The pamphlet was largely forgotten after his death, and the concept was rediscovered decades later. A force generated by sunlight warming an asteroid, too small to feel, operating too slowly to observe directly, accumulating over timescales measured in decades, eventually pushing a rock onto a different path through the solar system. For Apophis, measuring this effect was not optional. It was the final variable standing between uncertainty and confirmation. The observations came from the Goldstone Solar System radar in California and the Green Bank Telescope in West Virginia in 2021. Radar astronomy works by transmitting a signal toward a target and measuring the returning echo. The precision achievable with these instruments is extraordinary. The round-trip travel time of a radar signal can be measured to within microseconds, which translates to positional accuracy of meters over distances of millions of kilometers. When the 2021 measurements were processed and the orbital calculations were updated, the result was a measured drift of approximately -70 meters per year. That number, that specific small negative value, was the answer everyone had been waiting for. The drift confirmed that Apophis's actual trajectory was offset from the keyhole, not by a vast margin, not by thousands of kilometers, but by enough. The uncertainty region, now constrained by the Yarkovsky measurement, no longer overlapped with the 610-meter corridor. The 2036 impact scenario was eliminated. On March 26, 2021, the European Space Agency officially removed Apophis from its risk list. NASA followed with its own confirmation. The statement was clear: Apophis poses no impact threat to Earth for at least the next 100 years. 100 years is a long time. It is not forever, but in the context of planetary defense it is enough. Enough time to build better observatories, enough time to develop deflection capabilities, enough time for the next generation of scientists to work the problem with tools we have not yet invented. The relief in the planetary defense community was genuine and earned. Years of observation campaigns, radar pings, orbital simulations, and heated discussions about measurement uncertainty had converged on a single clean answer. The negative 70-metre-per-year drift was not a guess. It was science working exactly as it is supposed to work, steadily replacing uncertainty with knowledge. But here is what the headlines missed when they reported that Apophis was safe. The 2029 flyby was still happening. That had never been in doubt. What changed was the impact probability. What did not change was the flyby distance, 31,600 kilometers inside the geostationary belt, visible to the naked eye from 2 continents, a 340-meter asteroid, roughly the size of the Eiffel Tower laid on its side times 2, passing through the operational zone of human satellites at several kilometers per second. This event will not harm us, but it will teach us things that no laboratory, no simulation, and no previous flyby has ever been able to teach us. Earth's gravity during the encounter will exert forces on Apophis that are approximately 50 times stronger than the asteroid's own self-gravity. Think about what that means for a moment. The thing holding Apophis together is weaker than what Earth will do to it during that pass. The asteroid will be squeezed and twisted and pulled by our planet's gravitational field, and the surface of that object will respond in ways that scientists are genuinely eager to watch. The flyby will turn Earth into a natural asteroid laboratory, and humanity, for the first time in its history, will have spacecraft in position to watch from up close. What those spacecraft find may determine how we defend the planet from the next one. Part 6. Earth is about to reshape an asteroid. When Apophis makes its closest approach on April 13th, 2029, Earth's gravity will be the most powerful force that asteroid has experienced since it formed. To understand why that is significant, you need to understand what Apophis probably is. Most asteroids of this type are not solid rocks. They are rubble piles, collections of boulders, gravel, dust, and smaller fragments held together loosely by their own very weak gravitational field and by cohesive forces between particles. Picture a pile of gravel shaped like a potato, held together more by proximity than by structural integrity. The gravel does not want to fly apart, but it does not take much to make it shift. The Moon creates tides on Earth through exactly this mechanism. Earth's gravity is stronger on the side of the Moon facing us than on the far side. That differential pull stretches the Moon very slightly. It also stretches Earth's oceans dramatically, which is why tides exist. The same principle applies to any object passing close to a massive body. The near side gets pulled harder than the far side. The object gets stretched. If the object is rigid, internal stresses build. If the object is a loosely packed rubble pile, things on the surface begin to move. During the 2029 flyby, tidal forces from Earth will pull at Apophis with a force roughly 50 times greater than the asteroid's own surface gravity. Loose material near the surface could shift. Boulders that have sat undisturbed for millions of years might roll. Slopes that were stable in the low gravity of deep space might suddenly exceed their angle of repose and slide. The asteroid could experience a kind of slow-motion avalanche across sections of its surface, exposing fresh material that has never been touched by the solar wind. Scientists are genuinely uncertain about how dramatic these changes will be, and that uncertainty is one of the things that makes this event so scientifically exciting. Radar observations will map the shape of Apophis before and after the flyby with extraordinary precision. If the asteroid's shape changes measurably, if a ridge shifts or a depression deepens, that tells us something fundamental about its internal structure. Is it a loosely packed rubble pile? A solid monolith? Something in between? The flyby will provide the most direct evidence available. Brightness measurements will add another layer of information. As surface material shifts, the reflectivity of different regions changes. Fresh material beneath the surface is often brighter than the weathered outer layer, which has been darkened over millions of years by space weathering. the gradual bombardment of cosmic rays and solar particles. If brightness variations appear after the flyby in patterns consistent with surface disturbance, that is observational confirmation of tidal reshaping, the asteroid's rotation rate may also change. If material migrates toward or away from the rotation axis, angular momentum is redistributed and the rotation period shifts. Scientists will be measuring the rotation before and after the encounter with enough precision to detect changes of minutes or even seconds. Those measurements feed directly into models of asteroid interior structure, the kind of models that matter enormously when you're trying to figure out how to deflect one. There is even a possibility of a visible dust cloud. If the surface disturbance is significant, loose material could be lofted into space around Apophis, forming a temporary haze that telescopes might detect. This would be the first direct observation of tidal disturbance on an asteroid in real time. And here is the deeper implication of all of this. Planetary defense is not just about detecting dangerous asteroids, it is about understanding them. The method you use to deflect a solid rock is different from the method you use to deflect a rubble pile. Push a rubble pile too hard, and you might shatter it into dozens of smaller objects, each on a slightly different trajectory. Some of those trajectories might still intersect Earth. You could turn one threat into many. Knowing whether an asteroid is monolithic or fractured, whether its interior is dense or porous, whether surface material is firmly consolidated or loosely scattered changes the entire engineering calculus of deflection. The DART mission gave us one data point from one asteroid. The Apophis flyby, observed by multiple spacecraft simultaneously, will give us a comprehensive portrait of a real near-Earth object at the moment Earth's own gravity does something to it. The results will take years to fully analyse. Those years, and the missions producing the data, almost did not happen the way they were planned. Part 7. 3 spacecraft racing to meet it. Humanity has never had this many eyes pointed at a single asteroid encounter. 3 separate spacecraft, each built by a different agency, each carrying different instruments, each arriving at Apophis from a different direction and at a different point in the encounter timeline, will turn the 2029 flyby into the most comprehensively documented event in asteroid science history. The first is Osiris-Apex. If that name sounds familiar, it should. Osiris-Rex was the NASA spacecraft that spent years at the asteroid Bennu, eventually landing on its surface to collect a sample and returning that sample to Earth in September of 2023. After the sample capsule was released, the spacecraft still had functioning instruments and remaining fuel. Cancelling the mission at that point would have been wasteful, the equivalent of parking a perfectly working car because the first road trip was finished. So NASA approved an extended mission, renamed it Osiris-Apex, and aimed it at Apophis. In November of 2025, the spacecraft executed a crucial gravity assist maneuver using Earth's own gravity to redirect it toward its new target. The physics of this is elegant. Instead of burning enormous amounts of fuel to change course, you use the planet's gravitational field as a slingshot. Osiris-Apex swung past Earth and came out heading toward Apophis on a trajectory that will bring it to the asteroid around the time of the 2029 flyby. The mission plan calls for the spacecraft to operate in close proximity to Apophis, mapping its surface in detail before, during and after the Earth encounter. The before and after comparison is the scientific centerpiece. If the flyby reshapes the asteroid, Osiris-Apex will document exactly what changed, down to the scale of meters. The second mission is Ramses, the rapid Apophis mission for space safety developed by the European Space Agency. Ramses is planned for launch in 2028 on a Japanese H3 rocket, a timeline that leaves very little margin for error. The spacecraft's goal is to arrive at Apophis before the flyby, spend time characterizing the asteroid's surface and structure while it is still undisturbed, then remain in observation during the encounter and continue monitoring afterward. Ramses is also carrying CubeSats, small secondary spacecraft that can be deployed independently to observe from different angles simultaneously. One proposal being evaluated involves a lander experiment, an attempt to place a small instrument directly on the asteroid's surface before the flyby and monitor how the surface behaves as Earth's tidal forces increase during the approach. The third mission is Destiny Plus, a Japanese Aerospace Exploration Agency spacecraft whose primary destination is the asteroid 3200 Phaethon, the parent body of the Geminid meteor shower. Destiny Plus is designed to fly past multiple targets, and its planned trajectory includes an Apophis observation opportunity around the time of the flyby. 3 spacecraft, 3 agencies, 3 countries, 3 sets of instruments, all converging on a single object during a single event. The coordination required to make this work is enormous. The scientific return could be transformative, and one of these missions almost disappeared before it got anywhere near Apophis. Part 8. The mission that almost became a ghost spacecraft. In early 2025, the White House released a proposed federal budget that included a reduction of approximately 25% to NASA's science programs. Budget proposals are not final budgets. They're opening positions in a negotiation, and agency budgets get modified substantially before they become law. But the proposals contained specific mission terminations, and among the casualties listed was OSIRIS-APEX. Think about the specific absurdity of that situation for a moment. The spacecraft was already in flight. It had already left Earth. It had already completed its gravity assist maneuver. It was already heading toward Apophis. The instruments were functioning. The communication systems were working. The trajectory was set. Terminating the mission at that point would not have destroyed the spacecraft. It would have simply stopped operating it, stopped downloading the data, stopped maintaining the software, stopped paying the team of scientists and engineers who were managing it from the ground. OSIRIS-APEX would have continued on its trajectory regardless. A functioning spacecraft loaded with scientific instruments, heading toward the most important asteroid encounter in history, transmitting data that nobody was listening to anymore. A ghost spacecraft. A very expensive piece of hardware doing exactly what it was designed to do, with no one on the other end of the radio link. The annual cost to operate the mission at that point was approximately $20 million per year. In the context of the overall NASA science budget, that is a small number. In the context of what the data could return, in terms of planetary defense knowledge, in terms of understanding the structure and behavior of near-Earth asteroids, in terms of preparing humanity for the next time an object like this shows up with an uncertain trajectory, $20 million per year is extraordinarily cheap. Several members of the United States Congress made exactly that argument. The mission had supporters who understood both the scientific value and the strategic importance of planetary defense data from this specific flyby. Funding was ultimately restored, and OSIRIS-APEX remained an active mission. But the episode exposed a tension that runs through the entirety of planetary defense as a field. The threat from asteroids is real, but statistically infrequent on human timescales. The funding required to address that threat is continuous and must be justified every budget cycle against the competing claims of immediate problems: healthcare, infrastructure, defense, education. These are all real priorities with real constituencies. An asteroid that is not going to hit Earth for potentially another century is a harder case to make to a budget committee. Other missions were also threatened in the same round of proposed cuts. The Chandra X-ray Observatory, one of the most scientifically productive space telescopes in history. Juno, the spacecraft currently orbiting Jupiter. New Horizons, which flew past Pluto in 2015 and continues to return data from the outer solar system. The common thread in all of these cases is that operating an existing spacecraft is cheaper than building a new one, and the scientific return on investment is often enormous. The near cancellation of OSIRIS-APEX is worth keeping in mind when you consider the following question: what would have happened if Apophis had not been confirmed safe in 2021? What if the uncertainty had persisted, and the 2029 flyby was still carrying some residual impact probability? Would the political calculus around that $20 million mission have been different? Almost certainly. The lesson is uncomfortable but clear. Planetary defense receives sustained attention when the threat feels immediate. When the threat feels resolved, the urgency fades. And there are asteroids out there that have not yet been found. Asteroids that will not announce themselves with a 2.7% probability published on a risk list. Asteroids that will appear in the sky with far less warning than Apophis gave us. One researcher decided to quantify just how fragile our certainty about Apophis actually was, even after the safety confirmation. The result was a scenario so unlikely that most scientists would never have bothered to calculate it. Part 9. The 1 in a billion disaster scenario. Paul Wiegert is an astronomer at the University of Western Ontario, and in 2024 he published a study that began with a question most of his colleagues had never thought to ask. What would happen if a small asteroid hit Apophis before 2029? The premise sounds almost comedic. You have just spent years confirming that Apophis is safe. You have published the measurements, closed the case, removed the object from the risk list, and then someone asks, but what if something bumps into it? Wiegandt's calculations focused on objects in the size range of approximately 3 meters in diameter, the smallest class of near-Earth objects that can meaningfully interact with a larger body. These objects are common. The inner solar system contains an enormous number of them. Most of them will never come close to Apophis. But in the volumes of space involved, and over the years remaining before 2029, the geometry occasionally allows for a close encounter. If an object approximately 3 meters wide struck Apophis at the right angle, with the right velocity, the momentum transfer could shift the asteroid's trajectory by as much as approximately 340 meters from its predicted path. 340 meters is not a large number in astronomical terms, but remember what we established earlier. The keyhole for a 2036 Earth impact was approximately 610 meters wide. A 340-meter shift in the wrong direction could push Apophis uncomfortably close to that corridor. The probability of this scenario actually unfolding is less than 1 in a billion. Wiegandt published it anyway, not because he thought it was likely, not because he wanted to generate alarm. He published it because planetary defense science is built on the discipline of quantifying every possible risk, no matter how small, and because the calculation revealed something genuinely useful. If such an impact occurred, it would almost certainly produce a detectable dust plume around Apophis, a visible sign of the collision that telescopes could observe when the asteroid comes back into view for ground-based observation in 2027. In other words, if the 1 in a billion scenario were unfolding, we would know about it 2 years before the flyby. We would have time to recalculate. We would have time to update the risk assessment. We would not be surprised. That is actually the most important part of the story. Not the scenario itself, but the fact that a scientist sat down and worked out how we would detect it. The entire philosophy of planetary defense rests on this principle. Assume nothing is too unlikely to model, maintain observation campaigns, look for early warning signals, and build enough lead time into your detection systems that you can respond to surprises. Apophis gave us 25 years of warning between its discovery and its flyby. That is a long time. Long enough to measure the Yarkovsky effect. Long enough to launch multiple spacecraft. Long enough to develop and test deflection technologies. Long enough to have the budget arguments nearly lose the mission and restore the funding. The 1 in a billion scenario is a reminder that orbital certainty is not the same as absolute certainty. It is a probability, maintained by continuous observation, vulnerable in principle to events we cannot fully anticipate, and protected by the discipline of never stopping to watch. The story of Apophis, from its discovery to its flyby, changed planetary defense permanently, not because the threat was real, but because the threat was real enough for long enough that humanity was forced to build the systems, develop the techniques, and create the institutions that might one day stop an asteroid that actually is coming for us. That transformation is the real legacy of this object. Part 10. The Planetary Defense Revolution. Before Apophis, planetary defense was mostly theoretical. That is not a criticism of the scientists working in the field before 2004. They were serious people doing serious work, cataloguing near-Earth objects, running impact probability calculations, publishing papers about deflection techniques that had never been tested and might never need to be. The intellectual framework was sound. The threat was real and historically documented. The evidence of past impacts was written into the geology of the planet in letters large enough to read from space. But there is a particular kind of urgency that only arrives when the abstract becomes specific, when the theoretical becomes a number on a risk list, with a name attached to it and a date circled on a calendar. That urgency was missing, and then it was not. Scientists understood that asteroid impacts had happened throughout Earth's history. The evidence was everywhere, and you did not need to be a geologist to find it. The Chicxulub crater buried beneath the Yucatan Peninsula in Mexico is approximately 180 kilometers in diameter, the scar left by the impact that ended the Cretaceous period 66 million years ago and took the non-avian dinosaurs with it. The Tunguska explosion in Siberia in 1908 flattened approximately 2,000 square kilometers of forest, when an object estimated at 50 to 80 meters in diameter disintegrated in the atmosphere above a remote region that happened, by extraordinary good fortune, to be almost entirely uninhabited. If the Tunguska object had arrived 4 hours later, the rotation of the Earth would have placed St. Petersburg directly beneath it. The threat was acknowledged by anyone who looked at the evidence honestly. The urgency was not, because urgency requires imminence, and nothing in the catalogue before 2004 was imminent. Apophis changed the urgency in a single calculation. The shock of a real object receiving a level 4 Torino scale rating in 2004 did something that decades of theoretical papers and historical impact records had not managed to do. It created political pressure, the kind that translates into budget lines and organisational charts and institutional mandates. When an asteroid with a name and a measured orbit and a published probability of hitting Earth in 25 years appears on a risk list at the highest rating ever assigned to a real object, the conversation changes. It moves from the journals into the briefing rooms. It moves from the astronomers to the administrators. It moves from the question of whether planetary defence is theoretically important to the question of what we're actually going to do about it. NASA established the Planetary Defence Coordination Office in 2016, more than a decade after the Apophis scare, but directly traceable to the institutional momentum it generated. The office centralised responsibility for detecting, tracking, characterising and responding to near-Earth object threats under a single organisational roof. Before its creation, planetary defence activities at NASA were distributed across multiple centres and programmes, with overlapping jurisdictions and no single point of accountability. The Coordination Office changed that. It coordinates with international partners. It maintains public communication protocols so that if a genuine threat is identified, the information reaches the public in a form that is accurate and useful rather than fragmented and alarming. It liaises with emergency management agencies about response planning, because the response to an asteroid impact, should one ever be necessary, involves not just scientists but logistics chains, evacuation planning, and governmental decision-making at the highest levels. These are not glamorous institutional developments. Organisational charts and interagency coordination frameworks do not generate the kind of public excitement that a comet falling into the sun generates. But they are the difference between a planetary defence system that exists on paper and one that can actually function under pressure. The most dramatic development in planetary defence since Apophis, however, was not institutional. It was kinetic, and it happened on September 26, 2022, at a distance of approximately 11 million kilometres from Earth. The Double Asteroid Redirection Test, known as DART, was the first mission in history designed to test whether humanity could intentionally change the orbit of a celestial body. The target was Dimorphos, a small moonlet approximately 160 metres in diameter, orbiting a larger asteroid called Didymos. The choice of target was deliberate and elegant. Because Dimorphos orbits Didymos, its orbital period around the larger body could be measured precisely from Earth by tracking the regular brightness variations as it passed in front of and behind its parent asteroid. By measuring how much that orbital period changed after the DART spacecraft impacted Dimorphos at approximately 6.1 kilometers per second, scientists could calculate exactly how effective the kinetic impact had been at redirecting the object. The experiment had a built-in measuring instrument, and that instrument was the orbit itself. DART had launched in November of 2021. It travelled for 10 months before its final approach, guided by an autonomous navigation system that identified Dimorphos in the camera feed and steered the spacecraft toward it during the last hours of the mission. The impact was intentional, precise, and terminal for the spacecraft. DART ceased to exist on contact. What it left behind was a crater, a cloud of ejecta, and a changed orbit. The result exceeded almost every prediction that had been published before the mission. DART changed the orbital period of Dimorphos by 32 minutes, a significantly larger change than even the most optimistic pre-impact models had forecast. The margin of improvement over predictions was not small. 32 minutes against a pre-mission best estimate of roughly 10 minutes represented a deflection efficiency that surprised the planetary defence community and forced an immediate revision of the models used to plan future missions. The explanation for the larger-than-expected result came from the ejecta. When the spacecraft hit Dimorphos, it did not simply transfer its own momentum to the asteroid like a billiard ball striking another. The impact excavated material from the surface and threw it outward in a cone of debris. That debris, carrying momentum of its own, pushed back against Dimorphos as it flew away, acting like a natural thruster operating in the opposite direction of the ejector flow. The total momentum transferred to the asteroid was the spacecraft's momentum plus the momentum of everything the impact threw off the surface. In a loosely consolidated rubble pile with abundant surface material available to be excavated, that additional contribution can be enormous. Humanity had successfully changed the orbit of a celestial body for the first time in recorded history. The sentence deserves to be read slowly because it is one of the most significant things our species has ever done, and it happened with relatively little fanfare outside the planetary science community. The European Space Agency's Hera mission, launched in October of 2024, travelled to the Didymos system to study the impact site in the detail that DART's brief terminal approach could not provide. Hera arrived in early 2026 and is currently in the process of characterising the crater left by the impact, measuring the mass and internal structure of Dimorphos through gravitational measurements and radar sounding, and assessing how the overall dynamics of the Didymos system changed as a result of the collision. The data from Hera will close the loop on the DART experiment, providing the ground truth measurements needed to validate the deflection models and refine the predictions used to plan any future mission that might need to redirect an asteroid under non-experimental conditions. The distinction between experimental and operational deflection is important. DART was a test. The target was chosen because it was convenient for measurement, not because it was dangerous. The conditions were controlled in the sense that the outcome did not matter for planetary safety. A real deflection mission would face a different set of constraints: a specific target, a specific required change in orbit, a specific deadline imposed by the geometry of the threat, and no margin for the kind of refinement that comes from studying the results at leisure afterward. Hera's data will make the next mission, if there ever needs to be one, significantly more likely to succeed. The International Asteroid Warning Network, known as IAWN, provides the coordination layer that connects all of these capabilities across national boundaries. It links observatories, space agencies, and research institutions in dozens of countries into a framework for sharing data about potentially dangerous objects in real time. If a new threat is detected tomorrow, anywhere in the world by any telescope in the network, IAWN is the mechanism through which that information flows to the people and institutions that need to act on it. It is the global early warning system that planetary defense requires, and that did not exist in anything like its current form before Apophis made the need undeniable. These are real institutions doing real work funded by real governments, staffed by real scientists who go to work every day and do the unglamorous, essential labour of watching the sky. 20 years ago, they did not exist in this form. The Planetary Defence Coordination Office did not exist. The DART mission had not flown. The Hera mission had not been conceived. IAWN was a much looser collection of individual programs without the coordination infrastructure it has today. They exist now, in the form they exist now, in significant part because of one asteroid discovered on a routine observation night in 2004 that briefly made the world realise the sky was not as safe as we had assumed. But the system is not complete, and the people inside it are the first to say so. The detection capabilities still have serious gaps that the current infrastructure cannot close. There are near-Earth asteroids in the inner solar system right now that have not been found, have not been named, and are not on any risk list because they have never been observed. The ones that concern planetary defence researchers most are not the largest objects, the kilometre-scale impactors that would cause global catastrophe. Objects that large are rare, and the survey programs have found most of them. The catalogue at the top end of the size scale is reasonably complete, and the news there is mostly reassuring. What keeps scientists awake is the middle range, objects between 100 and 300 metres in diameter, large enough to destroy a city or generate a regional catastrophe, small enough to have slipped through the detection nets of every survey program currently operating. This is the size class where the catalogue is most incomplete, and the consequences of a gap are most severe. A 140-metre object striking a populated coastal region would kill more people than most wars. A 200-metre object hitting a major metropolitan area would be a civilizational shock. These objects exist. We know they exist because the ones we have found tell us statistically that there are many more we have not found. Apophis was 340 metres, It was discovered almost by accident in 2004, 25 years before its closest approach, giving the planetary defense community a quarter century to observe it, model it, measure its Yarkovsky drift, rule out every dangerous trajectory, and build the scientific understanding that will make the 2029 flyby the most productive asteroid encounter in history. 25 years is a long time. It is enough time to do everything right. The next one might be discovered with 5 years to spare, or 2, or 6 months, or as Chelyabinsk demonstrated with uncomfortable clarity, 0. The systems we have built because of Apophis might be exactly what saves us when that object is found. The detection algorithms, the observation networks, the deflection techniques tested at Dimorphos, the coordination frameworks connecting agencies across borders, all of it represents a genuine capability that did not exist a generation ago. Although systems might need to be built faster, pointed more carefully, funded more consistently, and expanded to cover the size ranges and orbital regions that still represent blind spots in our coverage, there is a telescope under construction that might settle that question, and when it reaches full operation, the catalogue of near-Earth asteroids will never look the same again. Part 11. The asteroid we still haven't found. More than 34,000 near-Earth asteroids have been catalogued as of 2026. That sounds like a large number, until you understand how many are estimated to exist and have not yet been found. Scientists working in planetary defense do not talk about the catalogue as a completed project. They talk about it the way a doctor talks about a patient whose test results are only partially back. We know some things, we do not know enough, and the things we do not know are precisely the things that matter most. Astronomers define potentially hazardous asteroids, known as PHAs, as objects that are both large enough to cause significant damage and whose orbits bring them within a certain distance of Earth's path around the Sun. The definition has 2 components, and both have to be true simultaneously. An enormous asteroid in a stable orbit far from Earth is not a PHA. A tiny object that crosses Earth's orbital path regularly is not a PHA either. The dangerous ones are the objects that are both big enough to hurt us and close enough to our neighbourhood to have the opportunity. The current catalogue represents a solid majority of the largest objects, those over 1 kilometre in diameter. Planetary scientists are reasonably confident they have found most of those. A kilometre-scale impactor would be catastrophic, a civilization-level threat, the kind of event that rewrites history and possibly ends it for a significant portion of the species. The good news is that the discovery rate for that size class is encouraging. The surveys have done their job at the top end of the scale. The largest, rarest, most catastrophic impactors are mostly known, mostly tracked, mostly confirmed as non-threatening for the foreseeable future. Hold on to that reassurance for exactly one more paragraph, because it is about to become less comforting. The problem is the middle range. Objects in the range of 140 meters and larger are capable of causing regional devastation on a scale that is genuinely difficult to describe without reaching for comparisons that feel like fiction. A strike in a populated area would be catastrophic on a scale that defies easy imagination. The thermal pulse arrives first, a flash of heat intense enough to ignite fires across a radius of dozens of kilometers before the sound of anything has reached your ears. The blast wave follows, a wall of compressed air moving faster than the fastest wind ever recorded on Earth's surface, stripping structures, flattening forests, carrying debris at velocities that turn ordinary objects into projectiles. The ejector, material thrown outward from the impact site, rains back down over an enormous area. The potential for triggering secondary disasters, fires, infrastructure collapse, contaminated water supplies, overwhelms the response capacity of any single nation and strains the capacity of the entire international system simultaneously. An impact in the ocean near a coastline does not spare anyone. It trades the immediate blast damage for something slower, and in some ways more terrifying. Tsunamis propagating outward from the impact site, affecting coastlines that had no direct exposure to the strike itself, reaching populations who may have had no warning that anything happened until the water began to behave strangely. Fewer than 40% of potentially hazardous asteroids in this size range have been discovered. Let that number sit for a moment. Fewer than 40%. That means the majority of objects capable of destroying a metropolitan area, triggering a regional catastrophe, or generating tsunamis affecting millions of people are currently flying around the inner solar system without names, without tracking data, without orbital predictions, without anyone on Earth knowing they exist. We do not know where they are. We do not know how many there are precisely. We do not know when, if ever, their paths will cross ours. We have built a catalogue of the most dangerous objects in our cosmic neighbourhood, and we have filled in less than half of the relevant entries. Part of the detection problem is geometric, and understanding it requires thinking about where telescopes actually point. Ground-based observatories operate at night. They cannot observe the sky in the direction of the sun because the sun is overwhelmingly bright, washing out any faint object nearby. This creates a blind spot in our detection coverage, a region of sky that remains essentially unmonitored from the surface of Earth. Some asteroids spend significant portions of their orbit in exactly this region. Objects that live in that orbital zone can approach Earth from the sun's direction, emerging from the glare with almost no advance warning, giving observatories on the night side of the planet no useful lead time at all. The Chelyabinsk meteor in February of 2013 demonstrated exactly how severe this problem can be, and it did so in the most direct and uncomfortable way possible. An object approximately 19 meters in diameter entered Earth's atmosphere over Russia with zero advance warning. Not reduced warning, not minimal warning, zero. No telescope had tracked it, no risk assessment had flagged it, no alert had been issued to any government or emergency management agency anywhere on Earth. It simply appeared in the morning sky over the Chelyabinsk region, moving at approximately 19 kilometers per second, and exploded at an altitude of around 30 kilometers in an airburst that released energy roughly equivalent to 500 kilotons of TNT. The shock wave from that explosion shattered windows across an area of thousands of square kilometers. More than 1,500 people were injured, the majority from flying glass. Buildings were damaged. The event was captured on dozens of dashboard cameras and security systems, which is the only reason most people ever saw what it looked like. If it had happened over a city centre, rather than a region with the population density of Chelyabinsk, the injury toll would have been dramatically higher. 19 meters is tiny by planetary defense standards. An object that size would not appear on most risk assessments as a civilization-level threat. It is below the threshold that most surveys prioritize. Nobody was looking for it because objects that small are nearly impossible to catalogue comprehensively, and resources are directed toward the larger, more dangerous size classes. But it arrived from the direction of the sun, undetected, and it hurt 1,500 people on an ordinary February morning while they were going about their ordinary lives. Now imagine that same scenario with a 140-meter object. Same blind spot, same approach from the sun's direction, same zero advance warning. The difference in energy release scales with the cube of the diameter. A 140-meter object is not 7 times more powerful than a 19-meter object. It is orders of magnitude more powerful. The Chelyabinsk event was a demonstration of the problem. A 140-meter Chelyabinsk would be a demonstration of the consequences. The Near-Earth Object Surveyor mission, known as NEO Surveyor, is designed specifically to address this detection gap, and its design reflects a direct lesson from the geometry of the problem. It is an infrared space telescope that would be positioned at the L1 Lagrange point between Earth and the Sun, a gravitationally stable location that allows a spacecraft to maintain a fixed position relative to both bodies. From that vantage point, NEO Surveyor can look outward in directions that ground telescopes cannot, including the region near the Sun's glare that currently shields approaching asteroids from detection. Infrared detection is particularly effective for asteroids for a reason that is worth understanding. Asteroids vary enormously in their reflectivity. Some are bright and rocky, reflecting a large fraction of the sunlight that hits them. Others are dark, carbon-rich objects that absorb most of the light they receive and reflect very little. A dark asteroid is harder to detect optically because it simply does not shine brightly. But even a dark asteroid absorbs sunlight and heats up, and a warm object radiates heat in the infrared spectrum regardless of how little visible light it reflects. An infrared telescope sees the heat, not the reflection. It works equally well on bright asteroids and dark ones, closing a detection bias that has existed in optical surveys since the beginning of the field. The planned launch for NEO Surveyor is no earlier than 2027. Once operational, the mission would be expected to discover thousands of previously unknown near-Earth asteroids within its first few years of operation. Some of those discoveries will require immediate follow-up observations to determine whether any of them have trajectories of concern. The pipeline from discovery to orbital characterization to risk assessment will need to process a flood of new objects, and the systems for doing that are being built and refined in anticipation of exactly that challenge. The expectation is not that Neo-Surveyor will find something dangerous immediately. The expectation is more important than that. The expectation is that humanity will finally know what is actually out there, which is the essential prerequisite for knowing whether we need to do anything about any of it. You cannot defend against a threat you have not found. You cannot calculate an impact probability for an object without a name. The catalogue is incomplete, and Neo-Surveyor is the most direct path toward completing it. But even before Neo-Surveyor reaches its destination, another telescope is already changing everything, and when it reaches full operation, the number of known near-Earth asteroids will not grow by thousands. It will grow by tens of thousands, possibly more, in a span of time that will make the current catalogue look like a rough draft. Part 12, the telescope about to flood us with asteroids. The Vera C. Rubin Observatory sits on a mountain in northern Chile called Cerro Pachon, and it is not quite like any telescope built before it. Most observatories are built for one thing. They are pointed at a specific target, a galaxy, a star, a nebula, and they stare at it for hours or days, collecting every photon they can from that single location. The depth of that stare is the point. Rubin was built on a completely different philosophy, an understanding that philosophy is the key to understanding why what is about to happen in the southern sky will change planetary defense permanently. Most telescopes are optimized for depth, the ability to observe faint, distant objects in detail. Rubin is optimized for something different: coverage. Not depth, but width. Not staring, but sweeping. Its primary mirror is 8.4 meters in diameter, large enough to collect an enormous amount of light from whatever it is pointed at. But the instrument that truly defines Rubin is its camera. The LSST camera, which stands for Legacy Survey of Space and Time, contains 3,200,000,000 pixels. 3 billion. For comparison, a high-end consumer camera contains perhaps 50 million pixels. The LSST camera contains 60 times that, packed into an instrument the size of a small car, designed to capture an area of sky so wide that a single exposure covers roughly 45 times the apparent size of the full moon. Think about that for a moment. One photograph, 45 full moons worth of sky, every few nights repeated across the entire accessible southern hemisphere for 10 years. The operational plan is called the Legacy Survey of Space and Time, and its mechanics are worth walking through carefully because the scale of what it will produce is genuinely difficult to absorb. Every few nights, Rubin will image the entire accessible southern sky, not selected patches, not targeted fields, the whole thing. Over the course of 10 years, every single point in that sky will be photographed hundreds of times, building a time-lapse record of the southern heavens at a resolution and cadence that has never existed before. The resulting database will be one of the largest scientific datasets ever assembled by any observatory in any field of science. The database of images will be so large that analysing it manually would not merely be impractical, it would be impossible in any meaningful sense. A human team working continuously for centuries could not process the volume of data that Rubin will generate in a single observing season. So the entire pipeline, from raw image data arriving from the telescope to finished scientific catalogue available to researchers around the world, will be automated. Software systems trained on millions of examples will scan every image, compare it to previous images of the same patch of sky, and flag anything that has moved, changed brightness, appeared where nothing was before, or disappeared where something used to be. For asteroid detection, this is a paradigm shift so large that the word paradigm shift does not quite do it justice. Previous sky surveys, the best ones, the most dedicated ones, the ones that have built the current catalogue of more than 34,000 near-Earth asteroids over decades of work, could discover hundreds of new near-Earth objects per year in good conditions. That rate represented the frontier of what was technically achievable with the instruments and methods available. Researchers were proud of those numbers, and they should have been. Building a catalogue of tens of thousands of near-Earth objects from ground-based observations is an extraordinary scientific achievement. Rubin is expected to discover tens of thousands of near-Earth asteroids in its first year of full operation. Some estimates suggest that Rubin may catalogue more near-Earth asteroids in a single year than all previous surveys combined have catalogued across their entire histories. That is not a figure of speech. That is not optimistic rounding. That is the actual projected discovery rate based on the telescope's known capabilities and the estimated population of undiscovered objects in the size ranges it can detect. The number is real, and what it implies for our understanding of the solar system's population is something the planetary defense community has been quietly preparing for, while the rest of the world has not been paying attention. The implications for planetary defense are profound and in the short term somewhat paradoxical. More discoveries sound unambiguously good. More objects found means fewer objects hiding. But each discovery requires follow-up. When a new near-Earth asteroid is identified, its orbit needs to be confirmed with additional observations over days and weeks. Its size needs to be estimated. Its trajectory needs to be projected forward in time to determine whether any close Earth approaches appear in the calculations. All of that work requires telescope time, analyst time, and computational resources. In the short term, Rubin will generate enormous numbers of new objects requiring this kind of follow-up observation. Far more objects per year than the current global observation network has capacity to characterize individually at the required pace. The discovery pipeline will far outpace the ability of existing systems to process every new alert with the same level of attention. This is sometimes called the alert flood problem, and the astronomy community has been preparing for it for years, developing automated triage systems that can assess incoming discoveries and prioritize which ones require immediate human attention and which can safely wait in a queue. The prioritization is not arbitrary. Objects on trajectories that bring them close to Earth in the near term go to the top of the list. Objects in orbital regions associated with known hazardous families get elevated priority. Objects large enough to cause significant damage regardless of impact probability get flagged for rapid follow-up. The systems doing this triage are themselves products of machine learning, trained on the historical catalogue to recognize the signatures of concern. In the longer term, the alert flood resolves into something that planetary scientists have wanted for decades and never had: a complete census of the inner solar system. Not an estimated census, not a statistical extrapolation from a partial sample, an actual observationally confirmed catalogue of what is out there, what size it is, what orbit it follows, and when, if ever, it approaches Earth closely enough to matter. Objects that were statistically expected to exist but had simply never been detected will be found. The actual population of potentially hazardous asteroids will be known with precision, not approximated with error bars. The distribution of sizes, the frequency of different orbital types, the prevalence of binary asteroid systems, the abundance of objects in size ranges currently underrepresented in the catalogue. All of it will be mapped with a completeness that changes the foundation of every risk model currently in use. Some of those changes will be reassuring. Objects currently estimated to be rare may turn out to be even rarer than models predict. The catalogue may confirm that the solar system's hazardous population has been reasonably well characterized at the sizes that matter most. That would be good news, and it is a genuinely possible outcome. But some of those revisions will be uncomfortable. Orbital families currently thought to contain a few dozen members may turn out to contain thousands of objects that were too small or too dark for previous surveys to detect. The frequency of close Earth approaches in certain size ranges may be higher than current statistical models suggest. Objects currently labelled rare may turn out to be common enough that the concept of a rare asteroid encounter needs to be revisited entirely. The shape of our understanding of near-Earth space will be revised, and revised significantly, and the revision will be data-driven rather than theoretical. Rubin will not be telling us what the models predict. It will be telling us what is actually there, which is a fundamentally different and fundamentally more honest kind of knowledge. Rubin will also observe comets, transient events like novae and stellar flares, supernovae in distant galaxies, and objects that do not fit cleanly into any existing category. Its survey cadence makes it particularly sensitive to things that change, anything that brightens, dims, appears, or disappears on timescales of days to years. The same properties that make it powerful for asteroid detection make it a transformative instrument for the entire field of time-domain astronomy, the study of how the universe changes over time. Among the objects it will find are some that do not come from our solar system at all. Objects on trajectories that no local origin can explain, moving through the inner solar system on paths that lead back to other stars, carrying material from planetary systems we have never visited and can barely observe. The catalogue of interstellar visitors, which currently contains exactly 2 confirmed entries, may grow dramatically once Rubin is operating at full capacity. The universe passing through our neighbourhood, it turns out, is considerably busier than we realised, and we're only now building the instrument sensitive enough to see how busy it actually is. Part 13, The Interstellar Visitors Changing Solar System Science. On October 19, 2017, the Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system on a trajectory that could not be explained by any solar origin. Its speed relative to the Sun exceeded the local escape velocity, meaning it was not gravitationally bound to our star. It had not formed here. It had not been orbiting here for billions of years like the comets and asteroids we had always catalogued. It had come from somewhere else entirely, from another star system, carried across the interstellar void by dynamics we can model but cannot fully imagine, and it was passing through. It would leave again, travelling back into interstellar space on a hyperbolic trajectory, and the window to observe it was already closing by the time anyone realised what they were looking at. Scientists named it Oumuamua, a Hawaiian word that translates roughly as a messenger from afar arriving first. That name was chosen carefully. It acknowledged what the object was without overclaiming what it meant. A messenger, not a threat, not a visitor with intent. A piece of something from somewhere else, passing through our neighbourhood the way a leaf carried by a river passes through a town it has never heard of and will never see again. It was the first confirmed interstellar object ever detected passing through the solar system. It was also, from the first moments of serious scientific analysis, deeply strange in ways that generated more questions than answers, and have not been fully resolved to this day. The shape was the first anomaly. Oumuamua appeared to be elongated to a degree that looked unusual by the standards of objects formed in our own solar system. Estimates based on the way its brightness varied as it rotated suggested it was approximately 10 times longer than it was wide, a geometry more like a cigar or a flat pancake than the roughly spherical or modestly irregular shapes typical of comets and asteroids. Solar system objects form through accretion, the gradual accumulation of material under gravity, a process that tends to produce objects that are irregular but not dramatically elongated. Something 10 times longer than it is wide suggested either a formation process very different from what we know, or a history of violent collision and fragmentation that produced a shape our local population rarely exhibits. The shape was unusual. The acceleration was inexplicable. As Oumuamua moved away from the Sun, its deceleration did not match the predictions of gravitational models. Objects moving away from the Sun slow down as solar gravity pulls at them. The rate of that slowing is predictable and well understood. Oumuamua was slowing down less than it should have been. Something was pushing it, adding a small but measurable acceleration in the direction away from the Sun. The excess acceleration was not a measurement error. It was confirmed by multiple independent analyses from multiple research groups using multiple datasets. It was real. The search for an explanation produced a spectrum of hypotheses that illustrated both the creativity and the discipline of the scientific process. At the conventional end, researchers proposed outgassing, the same process that gives comets their tails, where ice sublimating from the surface produces jets of gas that act as tiny thrusters. This is a well-understood phenomenon and a natural first explanation for anomalous acceleration in a small solar system body. The problem was that Oumuamua showed no visible coma, no detectable outgassing signature, none of the optical or spectroscopic evidence that normally accompanies cometary activity. If it was outgassing, it was doing so in a way that left no trace any telescope could find. At the extraordinary end of the hypothesis spectrum, a paper from researchers at Harvard, including the astronomer Avi Loeb, proposed that the object might be a light sail of artificial origin, a thin sheet of material created by an intelligent civilization and propelled by radiation pressure from starlight. The paper was careful in its framing. It did not claim the object was artificial. It argued that the hypothesis was consistent with the data and should not be dismissed simply because it was unconventional. That framing did not prevent the paper from generating headlines globally and significant controversy within the scientific community. Some of it focused on the science, and some of it focused on the question of whether publishing such a hypothesis was responsible or sensationalist. The consensus that has emerged over the years since is more grounded. Oumuamua was most likely a fragment of a disrupted planetary body from another star system. possibly a piece of frozen nitrogen with properties similar to the surface material found on Pluto and other trans-Neptunian objects. A nitrogen ice fragment of the right size and shape would sublimate in sunlight at exactly the rate needed to produce the observed excess acceleration, and because nitrogen ice is nearly transparent, the sublimation would not produce a visible coma of the kind a water ice comet would generate. The math works, the physics is understood. The explanation is not exciting in the way the artificial hypothesis was exciting, but it is scientifically coherent and consistent with what we know about how planetary systems form and how they occasionally shed material into interstellar space. The artificial hypothesis has not been confirmed. It has not been disproven either, because the object left the solar system before it could be studied in sufficient detail to settle the question definitively. Most researchers consider natural explanation sufficient and appropriate. A small number continue to argue that the anomalies deserve more serious attention than the mainstream has given them. Science is not always a clean consensus, and the Oumuamua debate is a genuine example of a case where the available data genuinely does not fully constrain the answer. What happened next, however, moved the conversation in a different direction entirely. In August of 2019, an amateur astronomer named Gennady Borisov, working from his own observatory in Crimea, discovered the second confirmed interstellar object. It was designated 2I/Borisov, the 2I indicating its status as the second interstellar object confirmed in the modern era. Unlike Oumuamua, Borisov behaved in ways that were immediately familiar to anyone who had studied comets. It displayed a clear coma surrounding its nucleus. It developed a visible tail pointing away from the Sun. Its spectroscopic signature showed the chemical fingerprints of water ice sublimating in the heat of the inner solar system, exactly what a comet is expected to show. Borisov was strange in only one way: its trajectory. The orbit was unambiguously interstellar, arriving from outside the solar system on a hyperbolic path that no local origin could produce. In every other respect, it looked like an ordinary comet, which was in itself a remarkable finding. The implication was that comets, objects of ice and dust formed in the cold outer regions of planetary systems, are apparently a universal product of solar system formation. Another star somewhere in the galaxy had built comets the same way our Sun did, and one of them had been travelling for an unimaginable span of time before Gennady Borisov happened to point his telescope at exactly the right patch of sky on exactly the right night. Borisov was easier to observe than Oumuamua. It was detected earlier in its trajectory, giving observatories more time to collect data. Multiple telescopes around the world, including the Hubble Space Telescope, were pointed at it before it left the inner solar system. The data it returned was richer and more complete than anything obtained from Oumuamua, and it confirmed that interstellar objects, at least some of them, are chemically and structurally similar to objects in our own solar system. 2 confirmed interstellar objects in 2 years changed the statistical picture in a way that could not be ignored. Probability theory is unambiguous on this point. If interstellar objects passing through the solar system were genuinely rare events, the chance of detecting 2 in a 2-year window with the survey capabilities available in 2017 through 2019 would be extraordinarily small. The far more likely interpretation is that interstellar objects pass through the solar system with some regularity, and the reason we had never detected one before was simply that previous surveys were not sensitive enough, not fast enough, or not wide enough in their coverage to catch objects moving at interstellar velocities on hyperbolic trajectories. We were not looking in the right way. The objects were presumably always there. Some models now suggest that dozens of interstellar objects may be detectable per year with the capabilities of upcoming telescopes, particularly the Vera C. Rubin Observatory, with its extraordinary field of view and survey cadence. If that projection is correct, the solar system is far more thoroughly trafficked by material from other star systems than anyone had suspected before 2017. The question of what those objects are, what chemical and physical record they carry from their home systems, and what they can tell us about the formation of planetary systems across the galaxy becomes not merely interesting, but actively answerable with instruments we are building right now. Every interstellar object that passes through the inner solar system is a sample return mission we did not have to launch. It is a fragment of another world, delivered to our doorstep by the dynamics of the galaxy itself, carrying information encoded in its composition about conditions around a star we may never be able to visit directly. The universe, it turns out, is considerably more interconnected than the model we grew up with. The solar system is not an island. It is a port, and the traffic passing through it has been going on for billions of years without us noticing. We just got our first 2 glimpses of what has always been moving through the dark. Part 14. AI is starting to discover asteroids. The history of asteroid detection has always been a data problem. Not a telescope problem, not a funding problem, not a theoretical problem, but a data problem in the most fundamental sense. The telescopes collect light. The cameras convert that light into images. The images pile up faster than any human workforce can meaningfully process them. And somewhere in that pile, moving slowly against the background of stars, are the objects that matter. The challenge has never been pointing the telescope in the right direction. The challenge has always been finding the needle after the haystack has already been delivered. Telescopes collect more images than humans can analyze. A single night of observing with a modern wide-field survey telescope produces thousands of images containing billions of individual pixel measurements. Each image needs to be compared with previous images of the same sky region to identify anything that has moved or changed. Moving objects are the targets, but moving objects are also exactly what most sources of noise look like. A cosmic ray hitting the detector produces a streak. An airplane crossing the field of view produces a trail. A satellite reflects sunlight and appears as a moving point. A ghost image produced by internal reflections in the optical system mimics a faint asteroid with uncomfortable regularity. Separating real detections from false ones requires pattern recognition that is simultaneously sensitive enough to catch faint real objects and specific enough to reject the enormous volume of artifacts that share similar signatures. Promising detections require confirmation from multiple observations before they are accepted into any catalogue. A single detection of a moving object proves almost nothing. 2 detections on the same night establish a direction of motion. 3 detections over multiple nights begin to constrain an orbit. The confirmation process takes time, requires additional telescope observations that compete with other scientific priorities, and introduces delays between initial detection and the moment when anyone can say with confidence that a new object has been found. The pipeline from raw telescope data to confirmed new asteroid has historically been slow, labour-intensive, and hard-capped by the number of trained human analysts available to work through it. Machine learning has begun to change this in ways that researchers who have spent careers in asteroid detection describe as genuinely transformative, and they do not use that word lightly. The core capability that machine learning brings to this problem is pattern recognition at scale. Algorithms trained on millions of labelled astronomical images where human experts have already identified which detections are real and which are artifacts, learn to distinguish genuine moving objects from false positives with accuracy that matches or in some cases exceeds the performance of trained human analysts. The difference is not in accuracy alone, the difference is in speed and scale. A trained human analyst can process a certain number of images per hour with sustained attention. An algorithm can process the same volume in seconds, and it does not get tired, does not lose concentration after 4 hours of staring at star fields, and does not have good days and bad days. It applies the same learned criteria to the 10,000th image with the same consistency it applied to the first. Systems like those developed for the Zwicky Transient Facility in California have demonstrated that AI-assisted detection pipelines can find objects that would have been missed by conventional analysis approaches. The Zwicky facility surveys the northern sky repeatedly and generates an enormous number of alerts per night, each one representing a potential transient event, a moving object, a variable star, a supernova, or any number of other phenomena. Processing that alert stream with human review alone would be impossible at operational speed. The machine learning layer handles the initial triage, classifying alerts by type and probability, passing the most significant candidates to human attention while managing the rest automatically. The result is a detection pipeline that's faster, more consistent, and more complete than anything achievable with purely human analysis. In 2023, a machine learning system analysing archival images from the Dark Energy camera, a powerful wide-field instrument mounted on a telescope in Chile, discovered more than 100 previously unknown near-Earth asteroids that had been present in data collected years earlier. The images existed. They had been sitting in an archive, fully preserved, waiting. The asteroids were in those images, their faint trails crossing the starfields on multiple nights, carrying enough information to establish preliminary orbits. They had simply not been identified at the time of collection because the human analysts processing the data could not examine every frame with the required attention to detail at the required pace. The AI went back through years of archival data and found objects that had been hiding in plain sight for years. Some of those objects had been sitting undiscovered in the archive while the planetary defense community was operating without knowledge of their existence. None of the newly found objects turned out to be immediately dangerous, but the exercise proved something important. The limiting factor in asteroid detection has not been the telescopes, it has been the analysis capacity. And analysis capacity is exactly the problem that machine learning is designed to solve. The implications of this extend well beyond simply finding more asteroids faster, though finding more asteroids faster is itself enormously valuable. The deeper application involves what happens after an asteroid is found, specifically the process of determining whether it poses any risk and tracking the evolution of that risk assessment over time. AI systems can model orbital uncertainty propagation with a speed and continuity that manual methods cannot match. Orbital uncertainty propagation is the mathematical process of calculating how the uncertainty in an asteroid's current known position and velocity grows as you project that orbit forward in time. A newly discovered asteroid has a short observational arc, which means its orbit is only loosely constrained. The uncertainty region, the volume of space where the asteroid might plausibly be at any future date, starts large and shrinks as more observations come in. The question of whether any part of that uncertainty region overlaps with Earth's position on a given date is exactly what impact probability calculations are measuring. This is also exactly the calculation that matters for keyhole analysis. Whether a 2029 flyby trajectory intersects a 610-meter corridor is a question about orbital uncertainty propagation over years of flight time. If an AI system can continuously ingest new observational data and update the orbital uncertainty model in real time, the impact probability assessment is no longer a periodic product generated by a human analyst who sits down to run the numbers on a schedule. It becomes a continuously updated quantity, responsive to every new observation, always reflecting the most current state of knowledge. A warning system built on continuous AI-driven orbital monitoring is fundamentally more responsive than one built on periodic human review. The difference could matter enormously if a newly discovered object has a short window between discovery and close approach, which is exactly the scenario that the Chelyabinsk event demonstrated is possible. Further down the development curve, researchers are exploring AI systems that could take on an even more demanding role: autonomous deflection mission planning. The concept works like this. Given a complete characterization of an asteroid, its trajectory, its estimated mass, its inferred structural properties based on spectral type and density estimates, and its surface characteristics derived from radar and optical observations, along with a catalogue of available launch vehicles, spacecraft designs, and mission windows based on orbital mechanics, an autonomous planning system might identify and evaluate deflection options faster and more comprehensively than human engineering teams working through the same problem manually. This is not a proposal to remove humans from the decision-making process when it comes to actually launching a deflection mission. The decision to fire a kinetic impactor at an asteroid, or deploy a gravity tractor, or use any other deflection technique will remain a human decision with political and legal dimensions that no algorithm is going to resolve. But the upstream work of identifying options, evaluating trade-offs, modelling outcomes under different scenarios, and presenting decision-makers with a clear menu of choices and their consequences, that work is computationally intensive and time-sensitive in exactly the ways that AI systems are designed to handle. The preliminary versions of these systems exist in research contexts today. They are not yet integrated into operational planetary defense workflows, but the trajectory of development points clearly toward a future where they are. The question is how capable they become, and how quickly the institutions responsible for planetary defense choose to incorporate them. That question brings us back to something that no algorithm can resolve and no telescope can observe. What AI cannot replace is the sustained political will to fund the telescopes, the spacecraft, the observation networks, and the institutions that make any of this possible. The detection algorithms are only as good as the data fed into them, and the data only exists if someone has decided that building and operating the survey telescope is worth the budget line. The deflection planning systems are only useful if there is a deflection mission available to execute, and deflection missions require funding cycles measured in years and political support measured in consistency across administrations and election cycles. That remains a human problem. It has always been a human problem, and it is the same human problem that Apophis revealed most clearly, not the question of whether the asteroid would hit us, but the question of whether we would pay attention long enough and consistently enough to find out. The challenge of directing collective human attention toward the right risks at the right time, even when something more visually spectacular is demanding that attention, is not a data science challenge. It is not an engineering challenge. It is the oldest challenge we have, and we are still working on it. Part 15. The Real Lesson of Apophis. We began with a comet, Comet C/2026. A1 is falling toward the sun right now, and the world is watching it with the kind of collective attention that only spectacle can generate. The live streams are running, the forums are active, the comment sections are full of people asking the same question over and over: will it survive? It is a genuinely compelling question, and the answer is genuinely unknown, which is part of what makes the comet so watchable. Uncertainty combined with visual drama is one of the oldest hooks in human experience. We are drawn to it the way we are drawn to a fire, not because we need to be near it, but because something ancient in us cannot quite look away. The comet is either going to emerge from the solar corona as one of the most dramatic objects in living memory, a tail stretching across the sky, visible in daylight, the kind of event that gets remembered for generations, or it is going to quietly cease to exist somewhere in the sun's outer atmosphere, dissolving into a faint smear of debris that disperses without ceremony. Both outcomes are possible. Neither outcome changes anything for anyone on Earth. Either way, Comet C/2026 A1 will pass 143.8 million kilometers from our planet and continue on its way, carrying zero consequence for any human life, past, present, or future. The show will end. The sky will return to normal. And the thing that actually mattered during those same weeks and months will continue its patient approach, largely unwatched, largely undiscussed, carrying 2 decades of scientific history and the most important lesson planetary defense has ever produced. And then there is Apophis. Apophis was discovered by 3 scientists doing routine work on a June night in 2004. Roy Tucker, David Tholen, and Fabrizio Bernardi were doing what asteroid hunters do, scanning the sky, logging positions, filing data. The object they found was assigned a preliminary designation number. Preliminary orbit calculations were filed in the standard way. Nobody expected anything unusual. Most asteroid discoveries are not unusual. They are catalogue entries, coordinates and velocities, objects that will be tracked for a few weeks and then quietly confirmed as non-threatening before disappearing into the database. And then someone ran the numbers forward in time and noticed that the trajectory was pointing somewhere specific. Not at empty space, not at a comfortable miss distance, at Earth, on a specific date, with a probability that nobody in the planetary defense community had ever seen attached to a real object before. 2.7% sounds small. It is presented as a small number when people write about it, and the instinct to treat it as a rounding error is understandable. But think carefully about what 2.7% actually means in this context. A 1 in 37 chance that a 340-meter rock hits your planet is not a rounding error. It is not a footnote. It is the kind of number that demands action, that justifies emergency observation campaigns, that gets passed between scientists at all hours because nobody wants to be the person who saw it and did not tell anyone. The global scientific community responded with exactly the seriousness the number deserved. What followed was years of the most intensive observation campaign ever mounted for a single near-Earth object. Radar pings sent across millions of kilometers of empty space and timed to microsecond precision on their return. Arguments about measurement uncertainty that ran through conference presentations and peer-reviewed papers, and late-night email chains between researchers on different continents. Keyhole calculations that required simulating millions of possible orbital trajectories to determine whether any of them threaded a corridor only 610 meters wide. Yarkovsky effect models that tried to account for the tiny but cumulative push of sunlight on a rotating rock over years and decades, the painstaking accumulation of data, observation by observation, radar ping by radar ping, until the uncertainty region around Apophis's orbit finally shrank enough to exclude every trajectory that led anywhere dangerous. The process was not dramatic in the way the comet is dramatic. There was no single moment of revelation, no one image that captured it, no visual that could be turned into a thumbnail. It was science working the way science is supposed to work, which is to say slowly, carefully, and without any guarantee of the answer until the answer actually arrived. And then, on March 26th, 2021, the all clear came through. The European Space Agency removed Apophis from its risk list. NASA confirmed the result. The orbital calculations, now constrained by the Yarkovsky measurement from Goldstone and Greenbank, placed the asteroid's trajectory cleanly outside every dangerous corridor for at least the next 100 years. The threat was gone. But the all-clear did not end the story. It changed the story in a way that turned out to be more important than the threat itself. The object that had threatened to end a city, or a coastline, or potentially something larger, became the object that was going to teach us everything we needed to know about how to stop the next one. The 2029 flyby, which had once been the date everyone feared, became the most anticipated event in the history of asteroid science. Spacecraft were pointed at it. OSIRIS-Apex, already in flight after completing its sample collection at Bennu, was redirected toward Apophis on an extended mission. Ramses was designed from the ground up to arrive before the flyby and document the encounter in detail. Destiny. Plus planned its trajectory to include an observation opportunity. Missions were funded, nearly cancelled by budget proposals that did not understand what was being discarded, and then restored by legislators who did. An entire generation of planetary defense technology was tested, debated, and refined in the context of this one asteroid, which had gone from the most dangerous known object in the solar system to the most scientifically valuable one in the span of 17 years. On April 13th, 2029, a Friday, you'll be able to step outside after dark, look up at the sky, and watch it cross from one horizon toward the other. A mountain-sized rock passing between Earth and our own satellites, visible without a telescope, moving perceptibly against the background stars if you watch long enough, documented simultaneously by 3 spacecraft, carrying instruments that will record everything from surface temperature to rotation rate to the subtle reshaping of the asteroid's profile, as Earth's gravity does something to it that nothing has done since it formed. Every lesson that 2 decades of observation have produced will be concentrated in that single Friday night passage. The human tendency to be drawn to spectacle over statistical risk is not a character flaw. It is important to say that clearly, because the easy version of this story is a lecture about how we should all be paying more attention to the right things, and lectures are not what this is. The tendency to watch the comet instead of the asteroid is not a failure of intelligence or a product of laziness. It is a feature of the brain that evolved in an environment where visible threats were the ones that killed you. The tiger you could see was the one you ran from. The fire you could feel was the one that burned you. The probability distribution of a long-term statistical risks was not a survival tool for the people who built the cognitive architecture we are still running on. They did not need it. The threats in their world were visible, immediate, and responsive to the same instincts that make a comet falling into the sun impossible to look away from. But we are not living in the ancestral environment anymore, and the threats that matter most now are precisely the ones that environment did not prepare us to notice. An asteroid that will not arrive for decades. A detection gap that will only be closed by a space telescope positioned between Earth and the Sun. An automated analysis system that will discover thousands of new objects and require the institutional infrastructure to evaluate each one before the next one arrives. These are not threats you can see from your backyard. They are threats you can only understand through numbers, through orbital mechanics, through the patient accumulation of observations across years and decades, through a sustained collective decision to keep paying attention even when nothing dramatic is happening. The lesson of Apophis is not that we got lucky, though in a narrow sense we did. The lesson is that we paid attention, and that paying attention worked. The observation campaigns reduced the uncertainty. The radar measurements pinned down the Yarkovsky drift. The orbital calculations converged on safety. Science replaced fear with knowledge, and the knowledge in turn became the foundation for building something genuinely new, something that has never existed before in the 4.5 billion year history of this planet. The first real planetary defense system in the history of the species. It is incomplete. The detection catalogue is less than half full in the size ranges that matter most. The survey telescopes are still coming online. The deflection techniques have been tested once on a non-threatening target, under controlled conditions. The political will to fund the whole enterprise fluctuates with budget cycles and shifts in public attention. 25 years of warning is a gift that the next dangerous asteroid may not give us, and the systems we are building need to be ready for the object that arrives with 5 years of warning, or 2, or 6 months. The comet is beautiful. Watch it if you can, genuinely it might be extraordinary. But understand what it is: a distraction, a gorgeous and completely harmless reminder of how much more interesting the sky is than most of us remember to notice. The real work of protecting Earth from the universe's occasional carelessness is quiet, continuous, underfunded relative to its importance, unglamorous in the way that all genuinely important infrastructure is unglamorous, and absolutely essential in a way that will only become obvious if we stop doing it. Apophis is not the last visitor we will need to worry about. The solar system is old and crowded and indifferent, and the catalogue of what is out there is still being written. Apophis is just the one that woke us up. The question now is whether we stay awake.